Te farei un seminario in inglese?
Sì, in inglese è migliore, sì.
Però sono cose che introducono in italiano, mi sembra che siamo tutti italiani, quindi è un piacere avere qui Arturo Perrones dell'Università di Nuevo León a Monterrey, che sarà qui fino
la prima settimana di
dicembre, che sta nella stanza di Lucio Fanelli, quindi se per caso avete interesse.
Sì,
certo. Ha chiesto se ci sono altri seminari, comunicate anche a lui.
Per favore.
E appunto oggi ci parlerà della termodinamica e dei limiti del calcolo.
È così, grazie Franco, grazie mille, grazie per l'invito. Adesso questo è il seminario. Buonasera. So, Thermodynamics and the Limits of Computation. Okay. So, I will talk about the limits of computation. It's quite obvious the title of this talk. But also about some strategies to maybe overcome some of them at a certain extent, okay? So I will start with the energetic limit. I will start about talking about the energy and the analogies that you can draw between computer machines and actual machines, actual thermodynamic machines. And I'm sure that all of you are quite aware of this paradox. It's not paradox in the usual sense, but some kind of, let's say, mental experiment, ideal experiment may be developed by Maxwell. This is the Maxwell demon. Was devised by James Clerk Maxwell in the time at which everybody was talking about thermodynamics and thermal machines. And it's quite curious because this is before the time in which the theory about microscopic particles in the thermodynamic system was developed by Maxwell, by Boltzmann, sorry. I believe it's a little bit before that. So what is the idea of Maxwell? Let's suppose that you have a thermal bath in which you have particles at different velocities, and you have some agent, some microscopic agent like this demon, which can choose between high energetic particles and low energy particles, and decide which one goes to which side of the divide in the bath, in the closed space in contact with the heat bath. So you know, if without the demon, without the agent, all the particles will arrive to a state of equilibrium. But the paradox is, let's suppose that you can devise this microscopic agent, and what will happen? Well, you can arrive to a state that is always in a state far away from equilibrium, without the loss of actual work. Let's say without the increase in entropy. So what happens here? And this paradox was solved very much later by people working on the private sector. And this is now named after them. Von Neumann and Landauer was the one working, I believe, at Bell Labs. And von Neumann is the one from the von Neumann architecture of computer machines. And the solution of this paradox is that you actually generate entropy with the introduction of this microscopic agent. And this entropy is generated just because you have to have memory in order to, you have to store the information regarding the energy of each particle, just to choose between the low energy and high energy particles. So you must erase information in order to, at some point, you must erase information just to keep track of the particles, and that actually generates some real energy by the means of entropy. Okay? And this may have some very practical consequences because, as you, I'm sure you are all aware, the circuits are